Hi everyone, welcome to this week's tutorial. So the calculations for this isn't too difficult, but interpreting the question can be a bit tricky. So we're going to go through all of these. I'm going to leave probably 3.7 to do in class on Tuesday. So let's start with 3.1. So a piezometer is used to measure the pressure in a water pipe. If the water level in the piezometer is 200 ml above the center line of the pipe, determine the pressure at this point. Got the answers in here. We're going to go through the calcs now. So what we have is I have a pipe running some direction. At some point in here I have a piezometer. What it's measuring, remember it's always from the center line of the pipe. It is measuring here to here as 200 millimeters. Cool. So how do I work out the pressure in the pipe? Well, P is equal to rho GH. It's water. It's 1000 is the density times 9.81 times 0.2. What this would give us is our 1.96 kilopascals for the pressure inside. So that is this one here, 1.96. Alright, like I said, the actual calcs very straightforward. Just gets a bit trickier interpreting the questions. So let's go for 3.2. So another piezometer, got different relative density of the fluid this time. Alright, outside diameter 200 ml of the pipe, and we've got the fluid. So what's happening here is we've got a pipe diameter of 200. We're obviously looking at the center line, and we've got a fluid level in the piezometer of 256 above the outside of the pipe. So just have to interpret this a little bit here. So how this looks is obviously I have pipe running, have piezometer, the pipe continues. So the diameter of the pipe is 200 millimeters. Now the level of fluid is 256 millimeters to the outside of the pipe. What we're trying to work out is in the center line, the pressure here. So this is my H. Alright, so what I have, my pressure is equal to rho GH. I had the relative density of 1.2. So my density 9.81, and the height here is just converting to meters. 256 gets me to the outside, plus 0.1, 100 mil gets me to the halfway. What this works out to be is 4.19 kilopascals. Cool. Question 2 done. 4.19 kPa. Now 3.3. The same pipe we just looked at has a wall thickness of 8 millimeters. Determine the maximum and minimum fluid pressures in that pipe. So here I have a thickness of the pipe, and here I have a thickness of the pipe. So it's 8 millimeters. Same with here. Alright, so how do I work out the minimum and maximum? I'll just erase this in here. So we're looking at 3.3. So for the max, and the max pressure is down the bottom, on this bottom wall of the pipe. So P max is equal to rho GH. So back here with the same density, obviously it's the same fluid, 9.81 times by, well, I've got 0.256 gets me to here. 200 gets me to the outer wall. I want to come in 8 millimeters from there. So that's plus 0.2 subtract the outside wall thickness, which is hundreds, tens, ones. Alright, so what we work that out to be is 5.27 kPa. Alright, and now for the minimum. So P min. Same thing, rho GH. Minimum is going to occur at this part of the wall, so the top. So it's 1200 by 9.81 times by the height, which is 256 plus 0.08. 256 plus, let's go 8 times 10 to the negative 3. Alright, that will get us there. Good enough, or same. And we go, that is 3.11 kPa. Alright, so maximum pressure is obviously on this bottom face here. Minimum pressure is on the top face here. And how'd we go? 5.27, 3.11, and we are all good. Awesome. So let's go to the next one. We're looking at 3.4. Incline piezometer slopes 30 degrees to the center line of a horizontal pipe carrying water. Piezometer reading is 320 mil, measured from the center line of the pipe. What is the pressure at the center of the pipe? Cool. So how does this look? Well, I have something like this. My piezometer is on a slope. I have my pipe in here. So 30 degrees. From the center line of the pipe. So from here to wherever the fluid's sitting. Let's go here. Is 320 millimeters. What other information were we given? That 30 degrees. Cool. Let's work out the pressure. So in this one, because it's on a slope, the pressure is equal to rho g h. H is equal to x sine theta. So therefore the pressure is equal to rho g x sine theta. We were dealing with water, so I have 1000 times 9.81 times, this is x over here, 0.32, and the other thing we're trying to work out is, this is h, times sine of 30. This here works out to be 1.57 kPa. Alright, so these are the examples that we had in the notes, so I hope you all read them. Like I said, it's not difficult calculations to do, it's purely just interpreting these written questions. So how do we go? 1.57 kPa. Beautiful. Let's move on. Let's go down here. Got enough room? Cool. 3.5. A vertical piezometer is placed at a certain point in a pipe sloping at 45 degrees. It's carrying a liquid of the relative density of 1.15. We've got a reading in there of 424 mil above the center line. Determine pressure at this point, so where it's sitting, pressure 300 mil down the line and 300 mil up. Easy. Alright. So what I have is my pipe is now on an angle. My pipe was on a 45-degree angle. So my center line runs through here. My piezometer comes up perpendicular. Come straight up. It's not very straight, Nathan. Sorry, that was a bad drawing. Yeah, it's a bit better. Not really. That's okay. So H from here to here is 424. Let's just check. Yep, 424 above the center line. Awesome. I have an RD, I'm just going to write over here 1.15. So to start off with, what is the pressure at this point? So for part A, well, pressure is equal to rho g h. RD. So what we have is 1150 multiplying this by 1000. 9.81 times the height. And this here gives us 4.78 kilopascals. That is the pressure at the center of the pipe. And let's go over here for B. How did we go? 4.78, beautiful. So work out the pressure 300 mil along the pipe downward from this point. So downward is running this direction, upward is this direction. So it's down, and that's up. So how are we going to do this? Well, it's on an angle, so I know to work out my new H, the difference here, I have to worry about the slope. So H is going to be equal to this initial height plus the difference. If I move down here, so from here to here, I'm adding in, this is my new H. I'm going to call it Z. So H is going to be equal to 424 plus Z, 424 millimeters, plus, where Z has to be equal to X sine theta, which is the vertical component. So I'm moving 300 millimeters down, so 300 is my X, 424 plus 300 sine of 45, which means my new H is 0.636 meters, converting it back to meters. Once I've got this, I can calculate my pressure, rho GH, 1150, 9.81 times by my new H, 0.636, and the new pressure that I get 300 millimeters down the line is 5.27 kPa. No, it doesn't. I cannot use my calculator. Sorry, that should be 7.18 kPa. Cool. That's better, 7.18. So now we're going the other direction. It's going back up. So what we do here for part C, my H is equal to 424 subtract Z going the other direction, so it's going to be 300 sine 45, and what this here equals is 0.212 meters. P is equal to rho GH 1150 by 9.81 by 0.212, which is 2.39 kPa, going the other direction. So this time now we're up here somewhere. So we're 300 mil up here. It is this difference, this distance here. This is my new Z. Alright, so first one was where it sits, second one was 300 millimeters down this way, third one was 300 millimeters upstream. Beautiful. Alright, 3.6, a couple more to go. So like I said, we'll miss 3.7, we'll do 3.6, we'll do 3.8, 3.7 we'll do in class. So 3.6 is what I'm going to be looking at now. So what is it? Well, a mercury manometer is used to measure the pressure of oil, relative density of 0.9 in a pipe. The interface level is 300 ml below the center line, blah blah blah. The level in the open limb is 125 ml above the interface level. Determine the oil pressure in the pipe. Now remember, mercury, RD of mercury is 13.6. So that's what we're going to assume here. So our first thing to do is to set this drawing up. So I have pipe running this way, some point along it, I have my manometer. Alright, it's not the best drawing in the world, but it will work. Some point up here in the center line, I have a pressure P. Below that, I have 300 mil. Alright, so where the interface is 300 millimeters. Then I have 125 in the open limb. So what does that mean? Well, that means across here, this is 300 millimeters. This here is 125 millimeters. All of this in here is our mercury. So I hope you all remember how to do this. We did this in class last week. Left hand side has to equal right hand side. So left hand side, right hand side. So my pressure here, rho GH, rho of mercury, 13.6 times 1000, 9.81 times the height, 125 millimeters. Remember, that is how much force it is to push this up. That should be open, not closed. Where was I? So the right hand side here for the mercury is equal to 16.6 kPa. Alright, so the next thing we need to do is do the left hand side. So my pressure over here is equal to the pressure at this point plus all of this in here. P plus rho GH is equal to P plus, now this was RD of 0.9, so my rho is 900, 9.81, my height 0.3, So this here is equal to P plus 2.65 kPa. So, like I said, the left hand side equal to the right hand side. The reason for that is, remember, at this point here on this x-plane, every point along this interface is the same pressure. So I can go P plus 2.65, 16.68. So therefore P is equal to 16.68 subtract 2.65 kPa. So therefore P is equal to, it's approximately 14 kPa, 14.03. Alright, and that's what we have here, 14 kPa. Beautiful. Alright, 3.8. Now this one's a bit more tricky. Just interpreting what's going on here, and what you're going to find is we have to go back to our first principles. Good fun. Alright, so what do we have? I have an inclined water manometer. It's used to measure the pressure of gas in a main. The open limb is included at 30 degrees to the horizontal. Reading on the inclined limb is 135 millimeters. Using the level and vertical limb as a datum. What is the gas pressure? We're aiming for 662 pascals. Right, how are we going to set this up? So again, you need to go through your notes, but how this thing looks, it comes up, comes down, and comes up, something like that. It's going to clash with my pipe because I can't draw. Let's redraw that, that looks horrible. Yeah, it's not much better, but it's not the easiest to draw on the computer, but we'll get there. Bit of time. So this is my pipe, dash line running through it, and at some point across here, I have 0.3, 0.2, and 0.1. Alright. What else do I have? Here to here. This should be my H. This here is at 30 degrees. And I know that the fluid in this point, from here to here, my X is 135 millimeters. So gas, and I have water, all three here. Alright, we do have examples of these in our books. Now, very important, remember everything along this X plane is the same pressure. So P3 equals P2 equals P1. Trying to work out the pressure at this point in the center line. So, that being said, how do we work this out? Well, my P at 1 is equal to P at 2. I know how to work out the P at 1. So, P1 is equal to rho GH, where H is equal to X sine theta, X being 135 millimeters. So it's equal to water, so an RD of 1, or density of 1000, 9.81 by 135 sine of 30. Punch this into your calculator. What you're going to end up with, 662 pascals. So that is the pressure at point 1, 2, and 3. Now what are we looking at? What's the rest of the substance here? Well, the rest of it is determine the pressure of gas in a main. So it's gas. All through here is all gas. All through here is all gas. So usually what happens is if we've got water, we calculate the pressure at point 1, which gives us point 2, gives us point 3. What we will then do is accumulate for all of the weight of the fluid above it, and we add P1 to the volume or the pressure here. Now that is good and well when we have water or a liquid, when our hydrostatic force is linearly increasing. Alright, so remember that. The further down we get, the greater the force. So our force is directly proportional to the height. Deeper it goes, stronger the force. Alright, now with our gas, what's happening? The force in the gas is uniform, which means, now I'll go with green. At this point here, this point here, this point here, this one, this one, this one, and this one, so let's number them. Let's go 1, 2, 3, 4, 5, 6, 7. For the gas being uniformly distributed like this, P1 equals P2 equals P3, P4, P5, P6, and P7. So what does that mean? The pressure is uniform, is the same at all points for the gas. So at this point here, at point 2, which is this point here, P2, P7, Nathan, I just can't read. So at P7, which is here, the pressure is the same. The pressure at the center line is the same. If it's the same, we can ignore the gas pressure. Alright, the pressure will be the same the whole way through. All of the force or the pressure of the gas in here is what is pushing the water to be at this level. So it is the same at the interface to what it is at the center of the pipe. So hopefully that makes sense. But basically what you'll find is P of the gas, so the pressure of the gas is negligible. Alright. Okay, I'll finish spelling that. So we can ignore it in this case because we have calculated it at this point. So I hope that makes sense. That is how we do all of the questions except for 3.7. We will do that in class on Tuesday. Alright, I hope it helps. Any questions, give me a buzz or flick me an email.